Okay, so let's look at why the Poisson process can be modeled as a random walk. And we're going to start off in the same place as we did for the construction of the Brownian motion. We're going to have a random walk with IID increments that are going to move +1 or -1. That's the starting point. But now we're going to do a couple of things. So on the picture below me there, you see what is starting to look like a Poisson process. I'll generate a few more paths there. So there it is. If we think of this as a random walk, it's moving kind of only one way. It's moving up. And so we have to somehow accomplish that. And the way we do that is we bias it. So we create a bias random walk. And we're going to do this in two different steps. One step is to add a drift. So I'm going to take this a random walk of increments plus or minus 1. This is kind of like the basis for the Brownian motion, this part right here. And I'm going to add mt to it. So I'm going to add the number of ones, a number of ones of exactly the same amount as in the sum. So it's kind of like adding this number is adding a 1 for each increment that appears in the sum. So each x increment, regardless of whether it's plus or minus 1, is going to be given an additional 1 here. And then I'm going to scale things by 2 for the reason you'll see in a minute. And the reason is that this new sum is going to look again like a random walk, but now the increments are actually going to be 0, 1 valued. So how do I know this? Well, if you sum things up right, each xl is just equal to 2 zl minus 1. You can easily see, for example, that when xl was minus 1, what happens? The z has to be 0, right? For this to be minus 1, for this side to be minus 1, the z had to be 0. And for x to be 1, conversely, z has to be 1. 2 minus 1 is 1. So you get this kind of bijection between the increments x and the increment z. When the increment xl is minus 1, the increment zl is 0. And when the increment xl is plus 1, the increment zl is also plus 1. So we were able, with this scaling procedure, to rewrite what is later going to be the Poisson process. This nmt is the process that I'm showing here, that I'm simulating in those pictures. That's exactly what it is. You see that it's moving up by amounts of 1. It never goes down. Now that the increments can only go up, the thing is never going to go down. So that's great. And the last thing we're going to have to do is we're going to, instead of having a coin flip determine the direction, plus 1 or minus 1, or in this case 0 and 1, we're actually going to use this parameter p here to determine the probability with which we move up. So z, in increment z equal to 1 is going to happen with probability p, and that determines on the picture below the probability with which we move up. So z0 is going to have probability 1 minus p, which means we stay on one of those planks. So for example, the one at 3, so y-axis on the picture at the level 3, we've stayed there for quite some time. All right, so this corresponds to the increment z being 0, a few amounts at a time, several kind of time periods at a time. And what we'll do eventually is we're going to have to take the probability p with which we do move up, and we're going to make it go to 0 as m, the parameter that's going to kind of scale everything for us and send the process to approximate the Poisson process in a nice way. We'll send that to 0. So we'll see why. We're going to explain all of this in the next few slides as to why we're making all these choices. I think the choice with respect to writing n or nm as a sum of these new increments that are 0, 1 valued, that's pretty sensible. I think we're going to have to dig into a little bit as to why we're selecting the probabilities for these quote-unquote coin flips, 0, 1 coin flips, in the way that we are. And the reason we do this is because of the following theorem, which is kind of the lesser known version of the central limit theorem for kind of Poisson random variables. So this is called the Poisson Approximation Theorem, and it sort of does the same thing for the Poisson distribution that the central limit theorem does for the normal distribution. So let's see how this plays out. So first, I'm going to design this random, or I'm going to use GM again, as I did in the case of the plus or minus 1 random walk. I'm going to define that to be n of 1. So here this just means the sum of m increments right here, right? At t equals 1, you would have the sum of n increments, each increment being 0 or 1. And we've already mentioned that we're going to now assign a probability Pm, which is going to go to 0 at some rate, which we'll see in a second. So the probability of moving up is going to be given by Pm. And as m increases, the probability of moving up becomes smaller and smaller and smaller. Let me see for a second what the value of m is here. So here the value of m is actually 1000 on the picture on the left. So that has gone quite a bit far in converging to the Poisson process. In any case, back to the Poisson approximation theorem. Here is the theorem, is that if you have this kind of biased random walk with increments of 0 and 1 shape, and their probabilities are behaving like this. So in other words, let's say we take Pm as some number mu divided by some integer m, and that integer m is the one used to construct the random walk to begin with. As m goes to infinity, this converges to mu. So one simple choice would just be to say, let's take Pm and make it equal to mu divided by m. That's one possibility. But as soon as this is met, you have the following convergence, and you can see here the Poisson distribution turns out, it gets kind of realized on the right-hand side there. In the central theorem, it was the normal distribution that popped out on the right-hand side. Now we're seeing in the Poisson approximation theorem the Poisson distribution. And so this is the what we're going to get for this new biased random walk that's only moving up. Once we take m out to infinity, we're going to see the convergence to not the normal distribution, but to the Poisson distribution. All of this is guaranteed by the Poisson approximation theorem. And you can see how I've picked up parameter t, the time t here. And the reason is that this GM here was defined in terms of t equals 1. And this n here is going to have less increments. So it's defined up here. It's going to have m times t, the integer part, increments. And so that leads to a pickup of time t on the Poisson distribution on the right-hand side. And the reason is kind of like, again, this reconciling the number of things in the sum versus the scale at which m goes to infinity. So this variable has mt number of things in it, and now we still have this condition, this one right here, the condition that m times pm goes to mu. But now the number of things in the sum is no longer m like it was in this case. It's now mt, and so we're going to write down what this is. So mt times pm is the same thing as mt divided by m times pm. So I'm just doing a little bit of rewriting, and all of this has to do with the fact that I don't have m things in the sum, I have empty things. So this is what I start with now to apply the Poisson approximation theorem. And now you very quickly see that the limit is no longer mu, it's mu times t. And that's what's responsible for the scaling on the right-hand side here. And also what's responsible for the behavior of the Poisson process, namely its distribution at any point in time, is going to be different. It's going to depend on the actual time value that we're looking at. So, this is kind of a summary of the same exact thing that we had for the Brownian motion. We later looked at increments. So before we looked at increments of the unbiased random walk, the one with increments in plus or minus 1. Now we're looking at increments with these ZLs here that take values in 0 and 1, so it's a little bit different, but all the properties of independence should still hold, and you again have the same trick as above, where we want to look at the distribution of the increment as m goes to infinity. Now it's going to be Poisson with parameter mu times t minus s. The t minus s comes from the number of things in this increment here. So the m n at time t and m at time t sums over empty things, and m at time s sums over ms things. The number of terms in this sum is therefore mt minus ms, which is what I'm going to multiply Pm by to apply the Poisson approximation theorem, and immediately this leads to mu times t minus s as the limit, which is how you know that it's the rate of the Poisson distribution. So you now have what the increments of this biased random walk, this Poisson random walk, they're tending to be distributed in the following way. That depends on the Poisson distribution and only on the length of time that passes for each increment. So I think we're getting to kind of the punchline here as to why we can model the Poisson process as a random walk. It starts off with a random walk with IID increments of 0 and 1. And when I say increment here, I mean discrete increments, right? We're still in kind of discrete time as it refers to the sum. So the increments for this random walk are of size 0, 0 and 1. We have this little correction for how often it goes up to 1. It's going to tend to go up by 1 less and less often as m goes to infinity, and it's going to have to happen with this kind of scaling. So Pm could be set to mu over m, where mu is the rate that you want for the Poisson process to have. And now we just kind of go through and ask all of the questions with respect to the definition that we set out to show. Does NM have counting paths? Yeah, sure. That's what they look like. I'm going to simulate a few more here. Let's see. Hold on. There we go. So all of these, these are all random walks. They're moving up by 1 each time. And so you do have a counting path, increasing step function of, with jumps of size 1. That's certainly true. The increments are independent. Yeah, definitely, because the ZLs were independent. And because the ZLs were independent, that's what makes the increments of this process, at least when you take m large enough so that the increments don't overlap, the increments of this on, over this continuous time scale will be again independent. And are they stationary? Yeah, we showed that this was the limiting distribution for each of the increments, and you can see that it only depends on the length of time that passes. So these are clearly going to be stationary. In other words, the starting point of the increment, which here is s, is not going to determine the distribution. It's only the duration of the increment, t minus s, that determines the eventual distribution. And so, that all of these observations lead to this definition, right? You can track it kind of one by one. Counting paths, yes. Independent increments, yes. Stationary increments, yes. Are they Poisson distributed? Yes, that was the Poisson approximation theorem. And the one kind of final thing that I want to talk about is this definition that we started with in the beginning, which had to do with a description of the Poisson process, a continuous time Markov chain, where we wait at each state for an exponential amount of time. So the question is that really what's going to happen, from this construction? So do we really get an exponential waiting time at each state, given this a random walk type construction? So if we were at state 3, do we wait for an exponentially distributed amount of time to get to state 4? And here's the way to kind of convince yourself that that's indeed the case. The first thing to do is to kind of start off at some state k, and we recognize that the next state has to be k plus 1. It's going to have to happen, and of course that happens as soon as the first random walk increment becomes 1. So you have this approximating random walk, and the increments are going to be kind of 0, 0, 0, and then all of a sudden there's going to be a 1, and we move up. And that's one reason for taking PM, the probability of this jump of size 1 to be smaller, is that we want to kind of stay at the particular state, and in this case it's state k, for some amount of time before we move on. And so when m large, you can kind of see that most of the ZLs are going to be 0, and a 0 means we stay at the state k. So we get a 0, we stay at state k, we get another 0, we stay at state k, another 0, we stay at state k, and then all of a sudden there's a 1 right here, and we move up to k plus 1. And what all of this is modeled by is clearly a geometric random variable, because what's happening is that we're just waiting for the first success being defined by ZL coming up 1, after a bunch of failures, which are going to be the ZLs being 0. And this is the distribution of that geometric random variable. You have n failures, so you want, for example, this time here, and this time is going to be, we're still in discrete time units. So if this waiting time between state k and state k plus 1 is n, that means we've had, we've had n failures, and that's their probability right here in the front, with 1 success probability, PM. That last multiplier here is responsible for the ZL coming up 1 as opposed to 0. So that's still in discrete time, but it's starting to kind of model how long we wait for within that framework. And we're going to have to move over to continuous time and show this is somehow going to turn out to lead to an exponential distribution. So first observation is this one. If you have this geometric random variable with parameter PM, the probability that geometric variable exceeds some number n is just the product of the failures. So it's a product of the n times that we failed. And the way you see this is you use the definition, of course, and you write out exactly what this event probability is. It's just the sum over over this distribution here, starting from n out to infinity, and that's what it is. We're computing the tail of the distribution, so we're summing from n to infinity. And then it's a little bit of a manipulation to kind of take out enough things so that the remaining sum in the parenthesis looks like a geometric sum, which we know how to compute. If you look at the sum, the first term is going to lead to a 1. Then the next term is going to lead to 1 minus PM raised to the power 1, then raised to the power 2, and so on and so forth. And what you get is, in fact, this convergence, right? So this would converge to 1 over 1 over PM, right? That's what this converges to. It's actually 1 divided by 1 minus PM. So that's how this factor gets canceled out. And what remains is just this multiplier here, which gives us this property. And now we need to switch over to continuous time, which what I did here by skipping ahead a little bit. We're going to put things on a continuous time scale. So we're going to take some fixed continuous time length h, and we're going to ask how long is it, what's the probability that this geometric variable exceeds our time mh, right? Everything, to get from discrete time to continuous time, you just have to multiply by the continuous time. That's what we did in here, right? So we're putting things on a time scale of t time units. So we're taking mt things in the sum. We're going to do the same thing here. We're going over to continuous time. We're going to look at a time interval of length h, and we're going to ask what's the probability that we wait longer than this thing. Well, immediately from this identity, you go to a limit that looks like this. So all I did here was plug in PM, right? And PM is equal to mu over m, right here, for example. So this step to this step should be fairly straightforward. I just plugged in PM into this calculation here. And the next thing is to recognize that this is really, in the limit, going to approach an exponential. So this is basically, by the definition of what an exponential is, I first have to multiply and divide by the h time unit to get things to kind of square away in terms of the power that I'm using, mh, and the divisor here. But if you look, this is exactly what the property of the exponential is. This limit directly translates to this exponential, and this right away tells you that the random variable of interest, which is this geometric random variable tau, how long we wait before going from state k to state k plus 1, as m goes to infinity, becomes the exponential distribution once time is scaled appropriately. So, even that part of the kind of that property of the process translates over pretty well, or exactly. It translates over exactly when we start from the random walk, Poisson random walk type definition. So that's the end of this clip, and I'll follow up now with a bunch of calculations that are useful for dealing with a Poisson process.